UCT.
Thank you very much. Thanks to the organizers for putting this together and for including me in this meeting. I was a little surprised. I've always perceived England as home country of politeness and good manners, and I was surprised with the rather explicit way they offer to deal with cheeky co-authors or evil chairmen, and you have them individually. So let's hope it doesn't come to this. All right. Plan of campaign is to first repeat Stuart's talk and then George's talk, and if time permits, in the end, I'll add a little bit on top of that. So definition, we've already seen it. I was going to say twice, but that's an overstatement. So if A is a C-star algebra, then the nuclear dimension of A, smaller n, means there are diagrams like this. You have A, and then you have a finite dimensional C-star algebra. You have a map from A to F, psi, and this is CPC. And you can write F as sum of n plus 1 finite dimensional C-star algebras, and then for the map upwards, phi, you can write this as a sum of n plus 1 maps phi I equals 0 to n, and these are CPC order 0, i.e. they preserve orthogonality. And then the nuclear dimension of A is smaller than n if for every finite subset and in A and any tolerance epsilon strictly bigger 0, there is such a diagram such that phi composed with psi on this finite subset approximates the identity map up to epsilon. Okay? And then this number n plus 1 is the number of colors you need, and n is the non-commutative analog of covering dimension. All right, so we've also seen some examples. Let me very quickly run through them. Again, start with C of x cross z to the d. Say if the dimension of x is finite and alpha is free and minimal, and if d equals 1, then alpha doesn't even have to be free and minimal, and this cross product has finite nuclear dimension. In this situation, analogous statement holds for flows. C of x cross r. Again, this cross product will have finite nuclear dimension if the space is finite dimensional and the action is free and minimal. In the case of not necessarily finite dimensional spaces, you could, for example, consider the uniquely ergodic situation, and then the action will have mean dimension 0 automatically, and then again the cross product will have finite nuclear dimension. Okay, and then as was mentioned in Stuart's talk, you can look at C-star algebras of the form A tensor Z, where Z is this Jiangsu algebra, and this has finite nuclear dimension if A is separable, simple, unital, nuclear, and it should be just like this, but for the time being we also need a condition on the trace space, so the extreme boundary of the trace space is compact, could be empty. Okay, and then more explicit class of examples consists of Kunz algebras, ON, Kunz-Krieger algebras, OA, and all sorts of other graph C-star algebras, higher rank graph C-star algebras. Okay.
So what is the nuclear dimension of this Kunz-Krieger and the graph algebra?
It's 1. In the simple case, it's 1.
Oh.
Yeah.
But higher rank Kunz-Krieger algebras?
Yeah, it's 1. It's because they're simple. Because they're simple. So the actual value usually doesn't matter. It doesn't matter so much. It's only whether it's finite or infinite. You can. So this gives you a large stock of examples. You can ask a question. Take C of x cross G for again alpha free and minimal, and G say amenable and discrete, and then also for dimension of x finite, and then you can ask whether this has finite nuclear dimension. Always, it's well possible. I think it's extremely intriguing question. All right, this is what I want to say for now about nuclear dimension. Now let me tell you what the UCT is, or what it means for C-star algebra to satisfy the UCT. So A satisfies the UCT, Universal Coefficient Theorem. You probably want A to be separable, a separable C-star algebra. If the following holds, so take some other C-star algebra B, arbitrary other C-star algebra B, it needs to be sigma unital, or it's allowed to be sigma unital. And then you can take kk of A comma B, bivariant K theory of Kasparov, and then you have a map to the group homomorphisms between K star of A and K star of B, and this map is given by Kasparov product, and then and you can look at the kernel of this map, and then sometimes you can identify the kernel with x K star of A, K star of B, and I need a dimension shift somewhere. Let's put it here, K star plus 1. B. Yeah, that's true. Okay, and you want this sequence to be exact. So this is exact for every sigma unital C-star algebra B. Okay, and the UCT problem asks UCT problem or UCT question ask, does every separable nuclear C-star algebra satisfy the UCT in this sense? So does every separable nuclear C-star algebra satisfy the UCT? Okay, and one one issue with the problem is that we don't even have a candidate for a counterexample, and of course whenever you're able to describe a separable nuclear C-star algebra explicitly, it has to come from somewhere, from some geometric data, and then very likely you'll be able to prove that it satisfies the UCT along the way. Okay. And the other issue is that this is a yes/no question, and it's very hard to, or at least it's not completely obvious how to come up with intermediate questions with partial results or non-results along the way. And my task for today is to show you a few different points of view on this particular problem, and also try to advertise the problem and try to show you that this problem might not be so far from one or two problems you've already seen, at least in spirit. Okay, so why do I care in the first place? We've already had this on the board. It's a classification result. The class of A, separable, simple, unital C-star algebras with nuclear dimension finite and satisfying the UCT, and I want A to be not isomorphic to matrix algebras, so not finite dimensional. This class is classified by its invariant of A, and this is just K0 of A with the positive part and position of the unit. Then you need the trace space of A and the map from the trace space on A to states on K0 of A, it's canonical pairing, and of course you need K1 of A, and that's a complete invariant. and we've already seen that this condition of finite nuclear dimension, it's in many, it's not always true, but in many natural situations you just have this, and you might have it in much greater generality, whereas this UCT condition, this might be automatic, but we have no way of enforcing it. This not, unlike here, when at least when the trace space is not too bad, if it's not a Paulson simplex or something like that, then we can simply tensor on the Jiangsu algebra. You can take a taxi or take the elevator, pay a price, but price is changing the algebra, but still we end up with the result. We force everything into a classifiable class. For the UCT, there's nothing like that. Okay. I mean, well, you could always tensor on with something kk equivalent to 0, but that's, even I would consider that cheating.
That's too expensive.
That's too expensive, exactly. That's like, well, okay, right. In the finite case of this theorem, so when you also assume there are traces, then quasidiagonality is an important concept coming in. Oddly, quasidiagonality already appeared in the infinite case via Kirchberg's O2 embedding theorem. Already there, you have quasidiagonality of suspensions of C-star algebras coming up, but in the finite case, quasidiagonality appears in a much more explicit manner, starting with Sorin's local quantization technique, and then going to Lin's work on TAF, C-star algebra, so on and so forth. And so then question was for quite a while, or still is, when is a finite nuclear C-star algebra quasi-diagonal? And one answer, not a complete answer, was given. Paper with Aaron Tigricius, Stuart White, and myself, and that says that A be a separable C-star algebra, and I want this to be nuclear with UCT, and then I want a trace, in fact a tracial state, and I want this to be faithful. Okay, and then conclusion is that under these hypotheses, then tau is quasi-diagonal, and let me tell you what this means. It means that there is an embedding of A into, well, Q. This is universal UHF algebra. It's 2 by 2 matrices, tensor 3 by 3, tensor 4 by 4, tensor 5 by 5, and so on and so on. And it's a C-star limit of this construction. So norm closure. That's Q, and that's not quite enough. I want Q omega, where omega is some free alto filter on the natural numbers. Okay. So Q omega. This is just L infinity of Q. It's bounded sequences with values in the universal UHF algebra equipped with supremum norm, and then you mod out sequences such that the limit of this sequence along omega is 0. Okay, this is the C-star alto power Q omega, and this thing has a unique tracial state. So tau Q omega, let's call it, is a map of the complex numbers, unique tracial state, and for tau, the prescribed trace tau on A, to be quasi-diagonal, you want to be able to find an embedding of A into Q omega such that the composition this way is just tau. Okay, and I'm slightly cheating here, really, for the definition. I don't want this to be an embedding, but let me stick with an embedding and stick with a simple case for the time being. Or if tau is faithful, then it's going to be an embedding anyway. Okay. Okay, this is quasi-diagonality of traces, and then you can, as a corollary, you get something that's not related to simple nuclear C-star algebras really, and not directly related to classification, at least not as far as the statement goes. This says that Rosenberg's conjecture holds, and that says that if G is amenable and discrete, an amenable discrete group, then the reduced group C star algebra of G is quasi-diagonal. So this means you have these finite dimensional approximate representations of C star reduced of G, and they're approximate representations in the norm sense, not just in the L1 sense. All right, so then what I like to refer to as the quasi-diagonality question then would say, if A is separable nuclear and say stably finite, does it follow that A is quasi-diagonal, i.e. A embeds into Q omega? So this is, you can ask this without referring to traces, of course. Okay, and well, this says in the presence of a faithful trace in the UCT, it's true. And there are variations of this. You can decorate this with additional hypotheses. So you can ask the quasi-diagonality question for simple C star algebras, or you can ask whether all traces are quasi-diagonal, not only in the faithful UCT situation. And there are other variations of this. So I don't want to take the time to run you through the whole proof of this, but I do want to arrive at a point where I can at least say how the UCT can possibly play a role in this. So the starting point for this theorem on quasi-diagonality is starting point for A unital is this. You take A and you would like it to sit in Q omega, so you want to embed A into Q omega. All right, that's what we would like to end up with, and that's too much to ask for to begin with. So let's take a cone over A, and then cone over A, that's contractible, and then by Voiculescu's result, of course, this embeds into Q omega. Fine, but if you just run through Voiculescu's argument, then you will not see the trace anymore. This will end up in a tracely small corner of Q omega. But if you use con and also result of Kirchberg-Rödam, then you can put this into Q omega in such a way that if you have again the unique trace on Q omega here, then you do have a map here, and this is then going to be a trace on the cone over A, and it's not just any old trace, it's the Lebesgue trace on the cone tensor, the prescribed trace tau on A. Okay, so using con and Kirchberg-Rödam, you can find an embedding of the cone over A into Q omega like this. Okay, and then we assume A to be unital, and that means that inside this cone we have just continuous functions on the half-open interval, and the sitting there tensor the unit of A. And we also have continuous functions on the open interval sitting inside there. So we have C naught of 0, 1 sitting inside here. And now what I would like to be able to is to flip this suspension, this open interval inside Q omega in a way that it commutes with A. Okay? That the flipping unitary commutes with A. So we make this precise. I would like to have a U in the unitary group of Q omega, and I want this to commute with A. Well, that's of course ridiculous, because A is not sitting inside Q omega. However, here I have this generating function of the half-open interval. So H, say, it's an element of C naught of 0, 1, and this is just the identity function on the interval. Okay, so I could ask this unitary to commute with H tensor A, but I want the unitary to do something that and then you will see that this is too much to ask for, but you can also multiply with 1 minus H times H tensor A. So these are going to be symmetric functions on the interval with values in A. All right. So I want a unitary that commutes with A in this sense, and such that it flips the interval, so such that U F U star is the same as F composed with the flipping automorphism of the interval, and this is for all F in C naught of 0. And I think of F such functions as sitting inside Q omega now. So
flipping that bar just a little higher, the upper bar. We can see the whole. Well, anyway, I can't see that whole. I've forgotten what was on the top. Well, that was, yeah, those are the. Which question are you addressing at the moment?
So now I'm addressing the proof of the quasidiagonality theorem, but really my purpose is to come to the point where the UCT is being used. Okay, and along the way I observed that finding a unitary like this would be enough. And of course this is too much of a mouthful. We can't do this right away. And then the idea is to do this, to implement this flip approximately, and that's where the stable uniqueness theorems of Lin and of Dadalat-Eilers come in. And then there's a certain dependence of an amplification size, the size of a matrix by which you have to amplify, and this dependence goes the wrong way, so you have to change order of quantifiers, and that's where the UCT comes in. And then making this jump, let me tell you what one would have to do, or one way to remove the UCT from theorem. I didn't number this. Let's call this theorem B, theorem A.
Reminding us that the theorem of data and algebras, and then use the UCT.
Yes, yes. So if I want to remove the UCT from theorem B, it would suffice to show that if you take kk of C naught of 0, 1, 0, 1, sorry, tensor A, and the first variable and second variable would be the product over, say, q omega, infinite product over q omega, and then you have this kk group, and then this maps to the product, just coordinate wise evaluation, to the product of kk C naught of 0, 1 tensor A, comma q omega, and you would have to show that this is injective, or showing that this is injective would be enough. Okay, and if A has the UCT, then this does in fact imply that this map is injective. Okay. All right. And this is one way of starting to try to remove the UCT from the assumptions of theorem B, but without any concrete idea of how to start. That's not so helpful. So instead, what I want to discuss sorry. What I want to discuss now, well, maybe I have time for one alternative approach. So maybe showing that this map is injective, that's not an easy task, and it's more than one needs to do to remove the UCT. You could also try to do the following: put something in between. So find E tensor A, and then find a map here, and find a map downwards, embedding of E tensor A into Q omega, and depending on what E is, this might be easier to find than embedding A directly, because you're allowed to kill off some K theory, and you could try to find a map of the half open interval into E tensor A. So you could ask to find a setup like this, E, kappa, and gamma like this, and then flip and implement this flip of this interval inside E directly. So then you don't have to worry about commuting with A, but then all these various properties, they're in friction. They're resisting each other. All right. Now, instead, you could also try to become a bit more modest and say, well, maybe I don't have to sort out the quasidiagonality question for all nuclear C-star algebras. Maybe for simple nuclear C-star algebras, maybe even for a smaller class, and maybe for this smaller class, I will learn enough to then attack the general case. And same for the UCT question, the UCT problem. And this is what I want to talk about now. So we've already seen definition of strongly self-absorbing C-star algebra. So D, again, a C-star algebra, separable, and not the complex numbers, and unital is strongly self-absorbing, and I abbreviate this as SSA, but really I've discovered only later that probably SSA really stands for super simple algebra. These are I mean, you can think of simple nuclear C-star algebras as C-star algebra analogs of the hyperfinite to one factor, but maybe these things are the real deal. They're the right thing in between. D is strongly self-absorbing if there is phi from D to the tensor D an isomorphism such that phi is approximately unitarily equivalent to the first factor embedding, identity of the tensor unit of D. Okay, and Stuart has already given us a list of examples. So it's M to infinity, M3 infinity, and so on, and then also the universal UHF algebra, and then there's one at the beginning. That's this Jiangsu algebra Z, and then there are also infinite ones, namely the Kunz algebra O infinity tensor UHF algebras, O infinity tensor Q, and then at the very end is Kunz algebra O2, the final object in the category of strongly self-absorbing C-star algebras. This is the initial ones. This is the final one. And then the question is, are these all? And in fact, this question is equivalent, well, to the question, if D is strongly self-absorbing, does it satisfy the UCT? Okay, if it's all these ones do satisfy the UCT, and we now know that if it's strongly self-absorbing and if it satisfies the UCT, then it falls under classification and then we're done. Then we know it has to be one of these. Okay. and now this UCT question, I mean, in this disguise or in the original, where is it? It's gone. In the original context, involve KK theory. It looks quite uncomfortable, but whether this list is exhaustive for this abstract class of C-star algebras, this is a very concrete question already. You can, of course, also talk about the quasi-diagonality question. Again, if you assume the UCT, then a strongly self-resolving C-star algebra is quasi-diagonal if and only if it is finite, and only if it has a trace. Without the UCT, then you can ask quasi-diagonality question for strongly self-resolving C-star algebras, and then due to the special structure of strongly self-resolving C-star algebras, this isomorphism or this embedding into Q omega that I was talking about, that I used to characterize quasi-diagonality, this you can then turn into an embedding of just Q. Okay, this is much smaller target algebra, so this is then equivalent to asking if D is strongly self-resolving and finite, which is the same as asking D to have a trace. Does this imply that D embeds into Q? And here, when I write an embedding, I mean a universal embedding. Okay. And this question I find particularly attractive for once, because there's an infinite version of this question as well. In quasi-diagonality, it's a very finite concept. You have an embedding into Q omega, there's traces around, and maybe there's no infinite version of that. I wondered about that, at least for quite some time. But in fact, when you look at it like this restricted form, then there is an infinite version indeed, and this just asks if D is strongly self-resolving, and if it's not O2, if it doesn't have trivial K theory, then does it follow that D embeds into Q? Well, that's too much to ask for, because there are infinite ones, but you can ask, does it follow that D embeds into O infinity tensor Q? Okay. So you can think of this question as an infinite version of the quasi-diagonality question.
So would that be the same as converging into an Alter power, if they're stable relations?
Yes.
If you could embed into the Alter power?
Yes. I mean, you can't phrase it in terms of stable relations, but because you don't have any generators for D. But yes, it's the same.
Oh. But you mean if it were self-absorbing and embedded into Q omega, then you wouldn't know it embedded into Q?
I would, yes.
You would know.
Yes. Okay, so then for a partial converse to theorem B, what's the partial converse to theorem B? I mean, theorem B, I'll think of this as UCT, take the UCT, take the right setup, round it, spits out quasidiagonality. You can ask, if you have quasidiagonality, do you get the UCT back in the right setup? Okay, and then a partial converse would be, so I phrase this as a question because I don't have a theorem. If D again is strongly self-absorbing and it sits inside M to infinity, inside the Car algebra. Okay, so not only does it sit inside Q, it actually sits inside M to infinity. Then does it follow? This is a question. Does it follow that either D is isomorphic to M to infinity, or you have that for all, say, natural numbers P, D also embeds into MP infinity. And this latter condition here, this is in fact equivalent for strongly self-absorbing C-star algebras to saying D is isomorphic to Z. Okay, this is what one might expect, and well, that's the question. It would be a partial converse to theorem B. It would not imply the UCT. It would obviously imply the UCT for D. It's one of these partial steps along the way that well, I believe if we can crack situations like this, then maybe along the way we'll learn enough to also handle the general case. But of course you can say this is a fairly special setup still, but more generally, you can ask what strongly self-absorbing inclusions of strongly self-absorbing C-star algebra D into another strongly self-absorbing C-star algebra E are there. Okay. And this setup, this almost has a subfactor flavor to it. And of course, for the time being, we don't have the right to really be interested in the position of D inside E when for this relation to the UCT problem, we don't even know whether there are any but the known strongly self-absorbing C-star algebras showing up in this context. But if it turned out that there are shadow or ghost strongly self-absorbing C-star algebras, then we'd be in business and we could study these inclusions in much more detail and maybe even come up with some combinatorial data which play a role. But that's a long time from now, I guess. So then, of course, you can ask, well, maybe for these strongly self-absorbing C-star algebras, the UCT holds, maybe it doesn't. But if it doesn't, then how to get started? How would we recognize it even if we saw it? Okay, so this is just a side remark, for a non-UCT example, it would be enough to find D strongly self-absorbing with torsion in K theory. In K0 or K1, doesn't matter. In fact, we can find an example with non-trivial K1 that would also do the trick. All right, and then you say, okay, how hard can it be to settle this question? Either show there is no torsion or find an example. This is
Because
again wide open.
because such a D couldn't be in the standard list.
Yes, yes. But the point of looking at strongly self-absorbing C-star algebras here is that in this case you don't have to worry about nuclearity. Strongly self-absorbing implies that the C-star algebra is simple and that it's nuclear. That was shown by Efros Rosenberg already.
They didn't show it implies something about K0 or K1.
No, I don't think so.
Well, I thought they showed it implied that K0 had to have rank 1.
Oh, okay, maybe.
But then maybe it says something about K1 too.
You need the Kuhn formula for anything like that.
Yeah. I mean, without the Kuhn theorem, Kuhn formula, you don't get anywhere. I don't quite remember what they said. Okay. So, and now as a last remark or bunch of remarks in this direction, let me show you another way of perhaps approaching this. So this is a theorem by Barlach and Lee based on Thu's work on amenable groupoids and the UCT. So they show if A is a C-star algebra and C in A is a Cartan MASAS. Cartan MASAS in the C-star algebra sense, as defined by Jean Renaud, but it's very similar to what Sorin mentioned in his talk. It's the same. It's the same in the C-star algebra context. Okay, so if you have a C-star algebra with the Cartan MASAS, then A satisfies the UCT.
Do you need some amenability somewhere?
That's probably true. Separable. Well, let's make this nuclear because I don't have the intention of lying to you guys, but okay. So if you have a Cartan MASAS, then you also get the UCT, because then you can write A as a groupoid C-star algebra with the Cartan MASAS as the diagonal. Okay, and then of course question is, if you have a strongly self-absorbing C-star algebra, do you always have a Cartan MASAS? But you can make this, specify this a bit more and say, suppose D is strongly self-absorbing and put D inside M to infinity, inside the Car algebra again, and say D has the same exhausts the K theory of the K algebra. So say K star of D is isomorphic to Z 1/2, and then question is, does D have a Cartan MASA under these circumstances? And then you might say, okay, this does look like something that one ought to be able to settle. However, there's some catches, and one of them is so let me make this a remark. Obviously, m to infinity has a Cartan MASA. In fact, it has more than one, and same goes for all the other ones, for all the other examples, and you can even show that Z has a Cartan MASA, and in fact you can show it has infinitely many Cartan MASAs. Z does have many. This was observed by Deely, Putnam, and Strong. And the way they do this is they write Z as a groupoid C-star algebra based on a pretty geometric construction, namely based on the existence of minimal diffeomorphisms on odd spheres. And then starting with this, they come up with a groupoid associated to this construction. And then they come up with spaces which are not quite odd spheres, but not so far off either. And then it's the dimension of these spaces which arise as the distinguishing feature for those Cartan MASAs in Z. And from this construction, you also see that you have Cartan MASAs of various dimensions inside m to infinity or inside UHF algebras, and this tells you that one shouldn't expect uniqueness of Cartan MASAs in any way, and in fact you should not even expect them all to be zero-dimensional. They can be wilder than one would hope for, but just the more even for an arbitrary strong self-resolving one, there should be at least one. Come on. Okay, I stop here. Thanks.
Any comments or questions? Everyone, thanks.